So today we're starting chapter 5. So most of our semester has been focused on the derivative, and that being the core concept of Calculus 1. Today we're going to switch to a different topic. We're going to start introducing a topic called the definite integral. It does relate to the derivative, but we won't get to see the relationship for a couple more classes. Okay. So today we're going to start talking about velocity and distance. And then you've got one more take-home quiz and then the final exam. Okay. The reflection project is just feedback on the course. It's not an actual math project. It'll be due at the final exam. I'll give it out Friday. Okay, so we're going to switch things up a little bit today. We're going to be calculating distance traveled given a velocity curve. And we're going to start with group activities today and do the demo in the last 15 minutes instead of the first 15. Okay. So you're going to start with our old zombie friends. And these graphs are time and velocity. Okay, so this is time, velocity. Okay, and I'm asking you to figure out how far they traveled. If you know how long they were traveling and you know something about their speed, you should be able to try to figure out how far they went. Okay. So I'm going to show you some notation that is how we describe mathematically what you just spent all of class doing. Okay, so what I'm going to do here is not new, it's just notation. Okay, okay, so the notation can be a bit heavy, but we're building up our math muscles. So just when you're doing an actual problem, remember you're just trying to find the area under a curve, right? So let me just pull up my highlighted big conclusion, right, from what you were just doing, is that if you have a graph of velocity, the total distance traveled is the area under the graph, right? And you can estimate the area under the graph using rectangles, right? You can get lower estimates and upper estimates by just breaking things into rectangles. All right, so that's what we're going to do here. I've got a generic function f over here, generic velocity function f of t. And I've broken it up into intervals, and instead of picking like 0 to 10 or 5 to 20, I'm going from A to B. Okay. So I'm picking a random x value A and a random x value B, and I'm trying to find the area under that curve. So I'm going to go from A to B. T is going to go from A to B, and I want to cut it into n equal pieces. So I'm going to go T1, T2, T3, blah, 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 up to Tn. So those are just my x values in between A and B, labeling them T sub whatever. Okay, so the width of each delta T, right, these little distances here. Okay, so I'm going from A to B, and I'm breaking it into n equal pieces. How do I figure out the width of each little delta T? They're what? No, the whole, there are n pieces, right? There's 1, 2, 3, 4, da 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 da, n pieces, but they don't have width n. These are delta T's. B minus A is the distance from A to B, right? That's how you find the distance between two numbers. So the total distance from here to here is B minus A. Everybody agree? Okay. And then we're going to break that distance into n equal pieces. So we divide it up into n equal pieces by dividing by n. So each little delta T here is B minus A over n. All right, so we approximate the total distance traveled, that is the area under the velocity curve, by using a left-hand sum or a right-hand sum. So in some of your zombie race problems, I had you get lower estimates and upper estimates, and that didn't always mean always use the left or always use the right. But in these examples, we're always going to use the left or always use the right. So if I want to use the left-hand endpoint to estimate distance traveled. So let's look at this first interval, T0 to T1, this very first interval here. I'm going to use the left endpoint of that interval to come up with a speed that I can assume that this zombie was running at for the entire interval. So I'm just going to use the left endpoint. Okay. So this rectangle, the area of that rectangle tells me how fast the zombie traveled on that interval. Okay. So the area of this rectangle is just base, which is delta t, right? That's delta t, times the height, right? What's the height of that rectangle? F of t0. Yeah, it's just the function value at t0, at that first value. How far? Because this function tells you how fast, right? So the function value, f of t0, that tells you how fast, right? And then this delta t tells you how long, right? So if you know how fast you were going and for how long, you multiply those together, which is also saying get the area of that rectangle, tells you how far. All right, so that's my first rectangle. F of t0 times delta t gives you the area of the rectangle or the distance traveled on that interval. So my next interval from t1 to t2, again, I'm going to use the left endpoint to come up with a speed that I was traveling for the whole interval. Just assume that speed for the whole interval. And then the area of that rectangle tells me the distance traveled. Okay. Because again, the height of that rectangle is f of t1, which tells you velocity at time 1. Okay, so this is velocity. And delta t is time, right? When you multiply time times velocity, you get distance traveled, which happens to be the area of that rectangle also. So we just keep doing that all the way down. And then the very last rectangle, okay, so the very last rectangle, if I'm going to use, oops, okay, so I've got this last interval, tn minus 1 to tn. Use the left endpoint. You go up to the curve. We're going to use that speed to be the speed for the entire time. So the height of this rectangle is going to be f of t sub n minus 1. The second to last time point, that's why it's the n minus 1. Yep. Yes, left and right are different from low and high. Yeah. We're typically going to use left or right, just so that we don't have to really think too much about whether it's low or... not necessarily. Yeah, because like this function is both increasing and decreasing. So if you wanted to get a low estimate, you would have to constantly switch between left and right. And so we typically just pick one, just use left or just use right. That way there's less thinking. It's more algorithmic, right? So this last interval, when we're doing a left-hand endpoint, you use the second to last time point for the height times delta t. So again, you have a time times a velocity. So that's how you do the left-hand endpoint, left-hand sum. The right-hand sum looks exactly the same. It's just, I don't want this line go away. Oh well. We're just going to pick the right-hand endpoint to be our representative speed over each interval. So I'm just going to erase this. And I'm going to do it again for the right-hand sum. So again, we look at the first interval, t0 to t1. But this time, to figure out what speed we're going to use as our speed over the entire interval, use the right-hand endpoint. So you go to the right-hand endpoint, go up to the curve, and use that to be your speed over the entire interval. So this time, the width of your rectangle is still delta t, but the height here is f of t1, the right-hand interval, the right-hand endpoint of the interval t0 to t1. So that's why the right-hand sum starts with f of t1, but the left one starts with f of t0. And then the very last rectangle, okay, we're looking at Tn minus 1 to Tn. If you use the right-hand endpoint of this interval to get the height of the rectangle, go up to the curve, you get the height of the rectangle. This is delta t, is the width of that rectangle, the time we've been traveling. And then f of Tn is the height of that rectangle, because we used Tn, the right-hand endpoint, to get the height of the rectangle. So with the right-hand endpoint, you finish with f of Tn and not f of Tn minus 1. All right, let's talk about what happens if the velocity function is negative. What does negative velocity mean anyway? You're going backwards. Yeah, so forward velocity is positive, velocity is forwards, negative velocity is backwards. Okay, so we want to find the distance from the distance traveled from t equals 1 to t equals 4 using this velocity curve pictured. And then for the same interval, we're going to find the value of another d word that's related to distance traveled. So distance traveled, like if I walk 5 steps forward, 2, 3, 4, 5, right? And 2 steps back, 1, 2. I traveled a total of 7 steps. Okay, so that's in distance. Like if you were in a car, right, your odometer would count all of it as just distance, right? So that's what we're going to do first. So negative velocity is just going to count as distance. All right, so we can find the exact area of this one because we know some geometry formulas. We don't have to use rectangles. Okay, so the total distance traveled. Distance from, so let's do our positive velocity first. So we'll do t equals 1 to t equals 3, right? So that's the area under the curve from 1 to 3. Okay, so what's the area there? 1/2 base times height, so it's going to be 1/2 times 3 times 6, which is 9. Yes, thank you. And I was only supposed to go from 1 to 3, so I drew it wrong. Only supposed to go from 1 to 3. There we go. Okay, how do I find the height of that triangle? 1/2 base times height, area of the triangle, so 1/2 times 2 times 4 is 4. Okay, now the car or whatever we're tracking here continues moving, right? It just puts it in reverse and backs up or something. Okay. So we want to go until 4. So from 3 to 4 just drives in reverse. Okay, we're still counting that as distance traveled. Okay, so how much distance is there from 3 to 4? 1/2, 1 times 2. Distance from t equals 3 to t equals 4. Yeah, 1/2 times 1 times 2 would be 1. Okay. All right, so total distance is going to be 5. Total distance 5. The other side of the line. Oh, so I drew. So first you draw your interval, right? So on the x-axis, I draw my interval from 3 to 4, right? And then I just want to find the area between that interval and my curve, right? So that's going to be, that's always your base of your rectangle or your triangle. So then I just, the area between that thing and your curve. All right, so what's the other D word, right? If I take 5 steps forward, 1, 2, 3, 4, 5, and 2 steps back, 1, 2, what's the other D word I'm thinking of? No. Displacement, right. So if I do 5 steps forwards and 2 steps back, what's my displacement from where I started? 3 steps, right? So how do you figure that? How did you come up with the 3? Subtract the second one, yeah. So distance that's under the x-axis, right, negative velocity, moves backwards. So we consider that to have negative area, right? So displacement, we would say we went 4 in the forwards direction and then 1 in the backwards direction. That's -1. So my total displacement here is 3 units. So this generalizes anytime you have area under the x-axis. If the area between your curve and the x-axis is under the x-axis, we consider that to be negative area. Okay, so that finishes up the demo. If you weren't quite done with the activities, you can just go back there. Question? Yeah. Yeah. Yeah, if the curve were acceleration, the area underneath it would be velocity. It's a good hypothesis.